We've got a pretty epic normal distribution question here. Lots going on, including some conditional probability later on and some hypothesis testing. Let's get into it. Healthcare centre claims that the time a doctor spends with a patient can be modelled by a normal distribution with a mean of 10 and a standard deviation of 4. So I can write down, I'm not going to define it, but let's say that x is the time. Then it will follow a normal distribution with mean 10, variance would be 4 squared. That's always a good thing to write down, distribution itself. And remember, this would look a little bit like that, like a bell-shaped curve centered at 10. So some people are going to, like most people are going to be hovering around the 10-minute mark, but then it's going to kind of go down either side. But you could get people, for 20 minutes in theory and so on, but with increasingly small probabilities. Okay, and we're asked to use the model to find the probability that the time spent with the randomly selected patient is more than 15 minutes. The probability that x is greater than 15. We can use our calculator for this. What we're actually doing is, if that was 15, the calculator is doing a little integration and finding everything beyond that. So this is going to be normal CD. The lower is going to be 15. The higher, I'm a bit inconsistent with how I approach this, but I'm just going to write 10 to the 9 here, or just type in lots of 9s. Just make it a big number. Standard deviation is 4, and the mean is 10. And we get 0.10564, which I'm going to, of course, round to 3 significant figures, 0.106. Some patients complain that the mean time the doctor spends with the patient is more than 10 minutes. The receptionist takes a random sample of 20 patients and finds that the mean time is 11.5. Stating our hypotheses clearly, using a 5% significance level, test whether or not there's evidence to support the patient's complaint. So of course, in the sample, it has gone up, but we're using a hypothesis test to see if there's enough evidence at the 5% level that it would have gone up in the whole population. So H0 is going to be that the mean remains exactly the same. It's still 10. With H1, we're looking at whether it has gone up. So mu greater than 10. X is then the time that it would take, like as I kind of defined before. I'm not going to define it here. Sometimes I think it is good practice. I should have probably done it here. I just didn't because of space. I'm going to assume H0 is true. And it will follow that X forms the distribution that we've already written. But what we want to find out is something called the sampling distribution. Because remember, we're actually taking 20 patients, finding their time, and then finding the mean time. This gives rise to a slightly different normal distribution because we're getting loads of points on a normal distribution. And then we are averaging it out to a single value. That is not going to give us the same distribution. It's still going to be centered at 10, but now the spread is going to be much less because you're not going to get many points towards the outer ends if you're taking 20 values and average, and then taking an average. It's very unlikely you're going to get 20 values and end up around one of the tails. So the sampling distribution still follows a normal distribution of mean 10, but now the variance is 4 squared divided by 20. You divide through by n, which means the standard deviation is then 4 over root 20, and that is what we're going to need to be using in our calculation. So I'm going to find the probability that this x bar is greater than 11.5. Because here's, well, there's going to be a critical region somewhere, and we want to see if 11.5 is in it, basically. So if our probability is less than 5%, we're going to be saying, you know what, it's in the critical region. There's a sufficiently small chance of that happening due to natural variation. Okay, so we're going to reject H0. If it's greater than 5%, we're going to say, you know what, there's enough of a chance that that could have happened. We're outside the critical region, then we would not reject H0. Let's find out what happens. So it's the same sort of calculation, but this time my lower is going to be 11.5. Keep the upper as that. But now I need to change this to 4 divided by root 20. Again, the mean was the same. We get 0.0467. And that is 4.67%. It's actually less than the 5% threshold that we have set. This means we're going to reject H0. And there is sufficient evidence at the 5% level that the patient's complaint should be upheld, or that the mean is above 10. Okay, good work. And the health centre also claims the time a dentist spends with a patient during a routine appointment T can be modelled by this normal distribution here. Mean of 5, standard deviation 3.5. Using the model, find the probability that a routine appointment with the dentist takes less than 2 minutes. So that would be the probability that capital T is less than 2. When I saw this question, I immediately thought, well, time can't be negative, so should we include negative time or not? But we should. With the model, we should just put it in. But later on, they start kind of bringing that into the question. So now the lower is just going to be a large negative number. This time I'm just going to write lots of 9s. That's enough. Upper is going to be 2. Standard deviation 3.5. Mean of 5. And we get 0.19568, which I'm going to round to 0.196. We're then asked to find the probability that t is less than 2 given that t is greater than 0. This ends up being the probability that t is less than 2 or the intersection of the sets t greater than 0 divided by t probability that t is greater than 0. We've got this extra condition, and so dividing by it like scales it. It's there is a formula, of course, and you would have seen it in earlier questions in this paper if you're doing the whole paper today. And it's the probability of A given B is the probability of A and B divided by the probability of B. I'm not going to go into any more where that comes from, but this is what we need to do here. So what that means is that because it has to be greater than 0 and less than 2, it's just going to be between 0 and 2. So now my lower is 0, my upper is 2, and I get 0.1191. And then I'm going to divide by the probability that it's greater than 0. So now my lower is still 0, but I just need to make this a big number. We divide by 0.9234. And this ends up being 0.129. Running out of space, I've gone straight for 3 significant figures. Let's explain why this normal distribution may not be a good model for t. So the appointment time must be positive, and therefore for the normal distribution to be a good model, the answers for part 1 and 2 should actually match. The probability that t is less than 2 should be the same as the probability that t is less than 2 given that it's greater than 0, because we know that it is greater than 0. And they don't match very well at all. I wouldn't say it's not double, but it's about 50% more. So a significant part of the distribution is going to lie in the negative region, actually, the negative time region. And that means it may not be a good model. The answers, they're a bit more concise. They just say the current model suggests non-negligible probability of t values that are less than 0. Because of the difference in them, you can see it's this like 0.07 that's going to be um, below 0. And this is impossible, and that's why it won't be a good model. So some words along those lines is all about these two not matching. And why don't they match? It's because this one is getting a lot of the probability from negative time. The dentist believes that she cannot complete a routine appointment in less than 2 minutes. He suggests that the healthcare should use a refined model, only including values of t greater than 2. Because at the moment, yeah, you could have an appointment that was actually 0 minutes or something, or 1 minute, and the dentist is saying, no, that's not actually realistic. We need to put 2 as like a lower cutoff. And then we're asked to find the median for a routine appointment using this new model, given the answer correct to one decimal place. So what we essentially have, I'm going to talk through this in two different ways. This is how I thought about it. We've got our normal distribution, and currently it's centered at 5, will remain to be that. Now here's 2, and basically we want to eliminate this. This is gone. This just cannot happen anymore. And so what we need to do, like the area under the whole curve is 1. Let's find the area from 2 upwards. Probability that t is greater than 2. And then we're going to sort of scale it using that idea. Because if it was, say, 0.8, the median is going to be after 0.4. So we can just use that new scaling. That's what I'm trying to say here. So the probability that t is greater than 2, I don't think we've worked that out already. So we've got 2, we get 0.80431. So now if I want to find the median, it would be exactly halfway. And I could, so let me call this m for the median. I can then write down that the probability that t is greater than the median is going to be a half of this amount, 0.40215. So I haven't made it any more complex than that. I'm just like got rid of a load of the values. So the overall probability, like the scaling, is now, well, the entire area is 0.80431. I could scale it up and make it 1. I could like divide through and then use 0.5 for my median. But I'm just saying, you know what? My median is going to be halfway along this area. That's all I need to do here. Don't need to overcomplicate it anymore. So probability that capital T is greater than m is going to be this. And now I'm going to be using my inverse normal. So I'm just going to change it back. I can still use the same model here. It's going to be less than m, and it's going to be 1 minus that, 0.59785. And now we use the inverse normal and we'll get the value that we need. So area, 0.59785. All of that's the same. And we get 5.867. Or, asked for one decimal place, 5.9. It's just one other way to think about this final part. We could write down that the probability that t is greater than the median, given that t is greater than 2, now that is going to equal 0.5. This is using a similar approach to what I've done, but it's actually bringing in some scaling now. I'm like basically dividing through by this to make the probability under the curve 1 again. I just want to say this one more time. Yeah, so I'm basically saying we know that t is greater than 2, and that means that we're now trying to find the middle value of the remaining kind of distribution. So the probability that t is greater than m, given that t greater than 2 is 0.5. And then we can bring that together. So we know the median is going to be greater than 2. And when I therefore do the intersection, t's got to be greater than m and greater than 2. It's just going to be that it's greater than m. And then I'll be dividing through by the probability that t is greater than 2. Now, we actually get to the same place as before because the probability that t is greater than 2, I already worked it out, it's there. I would then times zero point 0.5 through by it, and I'd get the probability that t is greater than m is that 0.40215 again. And then we can do the 1 minus, like I did, and work out m from there. So I'm not going to finish it off, but that is like another way to think about it. I just like cut it off and found all of this probability and then went halfway. This one here, we're using conditional probability and setting equal to zero point 0.5. It gives the same outcome, but you might prefer one line of reasoning than the other. Okay, well done. That is quite a tricky end to this question.